All right, now we're looking back. Now we're looking at divisibility, and we're starting with an easy one, of course, to prove that 3 to the 4n minus 1 is divisible by 16. So we already know the 3 steps already. Step 1, for n equal 1. When n is equal to 1, what we're getting is 3 to the 4 times 1 is 4 minus 1. 3 to the 4 is 80. 1 minus 1, which is 80. Can 80 be divided by 16? Yes, because 80 can be written as 16 times 5. And so therefore, n equal 1 is true. Indeed, for n equal 1, the statement is true. So right, therefore, n equal 1 is true. Yeah, man. Let's look at for n equal k now. For n equal to k, this is what we have. For n equal k, this is now 3 to the 4k minus 1. And 3 to the 4k minus 1, this is equal to 16 times, call it x. 16 times x, where x is an element of integer. X is an integer. And we assume that n equal k is true. All right, we assume n equal k is true. Assume n equal k is true. Now, of course, now we need to do the real part now for n equal k plus 1. For n equal k plus 1, this is what we're going to have. So for n equal to k plus 1, we need to show that 3 to the, so it's going to be now 3 to the 4 times in bracket k plus 1 minus 1. We need to 3 to the 4 in bracket k plus 1 minus 1. We need to show this is divisible by 16. Now from this equation up here, you could make 3 to the 4k the subject. If you make 3 to the 4k the subject from up here, you see that 3 to the 4k is 16x plus 1. We're going to bear this in mind. This is 16x plus 1. Just to bear this in mind, because we're going to be using this step down here. We're going to be using it down here. So this is now equal to 3 to the 4k plus 4 minus 1. Nice. Now, by laws of indices, we know that we can separate the bases. And so we know that we can separate this to be equal to, this can be written as 3 to the 4k. This can be written as 3 to the 4k times 3 to the 4 minus 1. Yep, by laws of indices, we can break this up that way. But then what is 3 to the 4? 3 to the 4, 3 to the 4 is 81. And then guess what? We said that 3 to the 4k is what? We said 3 to the 4k is 16x plus 1. So in brackets, 16x plus 1. And then we subtract 1. So what does all of this work out to be? Well, let us see. All of this is going to work out to be, we'll plug in 81 times 16 in our calculator. 81 times 16 is 1,296 x. Then we'll plug in 81 times 1 is plus 81 minus 1. That works out to be 80. And so now we just factor out. We're trying to show it's divisible by 16. So we'll factor out 16. And so what we get is 81x plus 5. Yes, so we get 81x plus 5. And so therefore n equal k plus 1 is true. So thus n equal k plus 1 is true. Since n equal k plus 1 is true, good. All right, therefore you just write your conclusion somewhere right here. Then you conclude. Therefore, by mathematical induction, let's write the conclusion at the top. Just so we know what we would conclude, you have to write your conclusion. So your conclusion can sound something like, therefore, by principles of mathematical induction, the statement given is divisible by 16 for all, it says for all positive integers, so you can just say for all natural numbers. That's your conclusion. You just tell them that by mathematical induction, the statement given is true. It is divisible by 16 for all natural numbers. You can tell them that. Nice, that would be your conclusion. Nice, so that's an easy example. Let's look at a hard one now. So here's a relatively hard question. Show that 2 times 4 to the 2n plus 1 plus 3 times 3 to the n plus 1 is divisible by 11. This is a relatively hard question. So of course we start with n equal 1, that's step 1. So for n equal 1, we're going to get 2 times, this is 4 to the, n is 1, so 2 times 1 is 2, plus 1 is 3, that's 2 times 4 cubed, plus, this is now 3 to the, n is 1, 3 plus 1 is 4, and what does that work out to be? So we have 2 times 4 cubed times 2 plus 3 to the 4, that's 209. Is that 209? Yes, this is 209 according to my calculator, and 209 can be written as 11 times 19. And so since we can write it as 11 times 19, therefore n equal 1 is true. Yeah, man, so when n is 1, it is divisible by 11. N equal 1 is true. Next, we need to go to our assumption stage, which is for n equal k. So for n equal k, what we're gonna write now is that we have, this is now 2 times 4 to the, replace n with k. This is 2k plus 1 plus 3 to the 3k plus 1. Nice, that's what we have, and this is supposed to equal to 11 times some number x, where x is an integer. Nice, x is an integer, some positive integer is x. All right, and we're gonna assume that this is true. That's the most important thing. We assume true. Now, what I'm gonna do is, since we're going to utilize 3 to the 3k plus 1 later on, I'm going to rewrite this as 3 to the 3k plus 1. I'm going to make this the subject. This is going to be equal to 11x minus 2 times 4 to the 2k plus 1. Now, bear in mind, you could have made 2 times 4 to the 2k plus 1 the subject, but because it's been multiplied by 2, I didn't want to make this the subject. So we have this now. So this, bear in mind, we're going to use this in our n equal k plus 1 phase. So that's what I want us to bear in mind. We should always bear this in mind. We're going to bear this in mind. So now, for n equal k plus 1, for n equal to k plus 1, what we're going to be getting is, for n equal k plus 1, we're going to get 2 times 4 to the, this is now 2 times k plus 1 plus 1. This is now 4 times, this is 4 to the 2 times k plus 1 plus 1. That's going to replace n with k plus 1 plus, this is now 3 to the 3 times k plus 1 plus 1. Whoa, this look hectic, this look heavy, but don't worry, we're going to simplify it. This is going to work out now to be, now look at this now. This is 2 times, now 4 to the, this is 4 to the 2k plus 2 plus 1. So that's going to be 4 to the 2k. This is really 4 to the 2k plus 3 plus, over here going to work out to be 3 times 3 to the k plus 4. Now, of course, I want something with 3 to the 3k plus 1 to substitute. So this 3 to the 3k plus 4 not going to work. It's not going to work. So what am I going to do? I'm trying to try and get rid of that. So to get rid of it, this is what I'm going to do. Firstly, I'm going to break up 4 to the 2k plus 3 as well as 2 times. Since I had something with 2 to the k plus 1, I'm going to break this up as 2 times 4 to the 2k plus 1. Using laws of indices, it's 4 to the 2k plus 1 times 4 squared. When the bases are the same, we add the powers. Plus, break this up as 3 to the 3k plus 4, I can break this up as 3 to the 3k plus 1 multiplied by 3 cubed. Multiplied by 3 cubed. Because when I break it up like this, a good now, because look at this now. If you were to add back the power right here, you get back the 4 right here. If you add 2 and the 1, you get back the 3 right there. So we get back the same thing. Now, what are we going to do? To simplify this part, I know that 4 squared times 2, 4 squared is 16 times 2 is 32. So we're going to end up getting 32 times 4 to the 2k plus 1. All right, so we get 32 times 4 to the 2k plus 1. Then what are we getting right here now? This part right here, I know 3 cubed is 27. So we get 27 times 3 to the 3k plus 1. All of that hard work to get it back in terms of 4 to the 2k plus 1 and 3 to the 3k plus 1. When you get a question like these, try to get it back in these powers so that you can substitute. Now we can substitute 3 to the 3k plus 1 as 11x minus 2 times 4 to the 2k plus 1. Now we can do that. Now we're going to substitute that now. Substituting this, we're going to get that this works out now to be 32 times 4 to the 2k plus 1. 32 times 4 to the 2k plus 1 plus, this is now 27 times in bracket, this is now 27 times 11x minus, that's 11x minus 2 times 4 to the 2k plus 1. Yeah, man, that's what we end up get. And so all we have to do now is we're going to just now expand in. We're going to now expand in. We're going to expand in this, expanding this number. So now we're going to get, this is 32, by the way. Let's rewrite this 3 a little bit clearer, a little more clarity. That's 32. So what we get is 32 times 4 to the 2k plus 1. And then we have now this minus the 27 times minus 2, going to end up give us minus 54 times 4 to the 2k plus 1. Yeah. And then what we're going to have now is 27 times 11x, 27 times 11 is 27 times 11 is 297x. So now we'll finish. Now that we finish, all we need to do is factor out 11 to show that it is divisible by 11. So let's write it all the way up here. We're gonna write it at the top. So we're bringing all of this up to the top up here. It's the final step in it. So factoring out 11, because I know that 32 times 4 to the 2k and 54 times 4 to the 2k. If you want, we can clearly see that this is now 32 minus 54. That's going to give you minus 22 times 2 to the 2k plus 1 plus this was our 297x. That's what we get. And then clearly all you had to do now is factorize out your 11. You factor out your 11 and you're left back with, factoring out 11 from this, we're left back with, oh, this is 4, not 2. Factor out your 11, you're left back with minus 2 times 4 to the 2k plus 1 plus, when you factor out 11 from 297, we're left back with 27. All right. So this works out to be 11 times some number. So it still works out to be 11 times some number. Let's call it R. And so therefore, n equal k plus 1 is true. So finish. So you can write, therefore, n equal k plus 1 is true. Just to say we write it down, you would write, therefore, n equal k plus 1 is true. And then you can write, of course, thus, by principles of mathematical induction, the statement given is indeed divisible by 11. That's it. Nice and easy. Soft, capital T, soft. All right. Let's look at this one now. It says, given that the sequence is A1, A2, A3, A4, and A1 is 1, and AN is AN minus 1 plus 3 for n greater than or equal to 2, prove by induction for any greater than or equal to 2, AN is 3n minus 2. Now, first thing you have to start out with is this where them give you. They said for n greater than or equal to 2, so you have to start from n equal 2. You have to start from n equal 2. So from n equal 2, what you're going to get is A2 is equal to, plug in as 2 right here now, because this is the formula for AN. A2 is A1 plus 3. A1 plus 3. What is A1? A1 is 1. That works out to be 1 plus 3, which is 4. So A2 is 4. Now let's check to see if it is true with the next one now. So from this formula now, we're seeing that A2 is equal to 3 times n, where n is 2, minus 2, which is 6, minus 4, 6 minus 2, which is 4. And so what can we conclude? N equal 1 is true. Therefore, n equal 1 is true. Nice. What to do next? Now for the next part now, n equal k. So for n equal k, what we're going to have is this. We want to prove this, right? We want to prove that AK is equal to 3 times k minus 2. That's what we want to prove. AK is 3 times K minus 2. And so we're going to assume that this is true. For n equal K, you assume it is true. Nice. Then let's look at the final stage, the big boy stage, for n equal K plus 1. For n equal K plus 1, right? For n equal K plus 1, for n equal K plus 1, you're going to plug it into the recurrence relation formula. In the recurrence relation formula, n equal K plus 1 will give us AK plus 1. AK plus 1 is equal to, plug in n equal K plus 1 here, you're going to get AK. This is now AK plus 3. Nice, that's what we get right there. Then what is AK? AK, we plug in AK now. AK plus 1 is AK plus 3. What is AK? AK is equal to, this is now 3. What is AK? From above here, AK is 3K minus 2. 3K minus 2 plus 3. So let's see if it is true. This works out to be 3K minus 2 plus 3 is plus 1. That's what we're getting. All right? 3K plus 1. But look at this. If you replace n with K plus 1, what we want to prove, from this line right here, if we were looking at what we want to prove, what we would have wanted to prove is that AK plus 1 is equal to 3 times, in bracket, K plus 1 minus 2. 3 in bracket, K plus 1 minus 2. That's what we wanted to prove. And this would have still worked out to be 3K plus 1. So since we get what we want to prove, therefore n equal K plus 1 is true. So we can write, thus n equal K plus 1 is true. Once you show that that is true, you're done. All we need to do now is write our conclusion. So you write your conclusion right here. Let's carry it up here, write our conclusion. So hence, you can tell them that hence AN is equal to 3n minus 2. It's indeed true. AN is 3n minus 2. And this is for all n greater than or equal to 2. It's really true. Nice. All right, now let's look at an inequality proof, one of my favorites. We're going to do an inequality proof here. It says, prove by mathematical induction 2 to the n is greater than n for all positive integers. So first you start from n equal 1. For n equal 1, clearly we can see that 2 to the 1 is greater than 1. So that is true. This is definitely true. So n equal 1 is true. Then now, for n equal k, for n equal k, what we're going to be getting is 2 to the k is greater than k. And we're going to assume that this is true. We're going to assume that this is true. We assume true. Assume n equal k is true. Now that we assume n equal k is true, we need to look at n equal k plus 1 now. So for n equal k plus 1, let's see what is going to happen. First thing, write down what are we trying to prove. What do we want to prove? We want to prove now that 2 to the, replace k, n with k plus 1. We want to prove that 2 to the k plus 1 is greater than k plus 1. That's what we want to prove. This is what we want to prove. Or this is what we're required to prove. RTP, required to prove. We are required to prove this. So for n equal k plus 1, let's see how we can do that. You don't even need to write this, n equal k plus 1. You just need to prove it. So to prove it now, first we have to start with what we know. Starting with what we know 2 to the k is greater than k. Now what if I multiply both sides by 2? If I multiply both sides by 2, I would end up get that 2 times 2 to the k is greater than 2 times k. I multiply both sides by 2. By multiplying both sides by 2, I can then add the bases. Since the bases are the same, I can add the powers on the left-hand side to get 2 to the k plus 1 is now greater than 2k. This is now greater than 2k, right? But look at this. Now 2k is equal to k plus k. 2k is equal to k plus k. Yeah, man, 2k is equal to k plus k. But guess what? K must be greater than 1. K must be greater than 1. We prove for k equal 1. But k must be greater than 1. And so 2k, which is equal to k plus k, this part right here must be greater than k plus 1. K plus k must greater than k plus 1. Think about it. If k was 2, 2 plus 2 is 4, that's greater than 3. If k was 7, 7 plus 7 is 14, 14 must greater than k plus 1. So k plus k must greater than k plus 1. So that implies now that since we know that 2 to the k plus 1, we know that it is greater than 2k, which is k plus k. So we know that 2 to the k plus 1 is greater than k plus k. And we know that k plus k is greater than k plus 1. Then we can conclude that 2 to the k is indeed greater than k plus 1. So we can indeed conclude now that 2 to the k is greater than k plus 1. I really hope it makes sense. It really makes sense. So now you can write that therefore 2 to the k plus 1 is indeed greater than k plus 1. So we'll prove what we want to prove. All right, so we'll prove it, and then you write therefore n equal k plus 1 is true. Nice. So we can write thus n equal k plus 1 is true. Nice. Then you write your conclusion. Nice. That's all. Then you write a conclusion. Nice. Next question. This one right here says, prove by the principles of mathematical induction that n squared is greater than 2n plus 3 for a positive number where n is greater than 4. So for all positive integers from 4 and bigger. So look at your starting point. You have to start from n equal 4. So starting from n equal 4, what we're getting is 4 squared is bigger than 2 times 4 plus 3. That is definitely true. 2 times 4 is 8 plus 3 is 11. So this is definitely true. So this is definitely true. So therefore, thus n equal 4 is true. Yeah, man. Now for n equal k. For n equal k, what we're going to get for n equal k, we're going to get k squared is greater than 2 times k plus, this is not written properly, k squared is greater than 2k plus 3. Where, remember, you have to state that since n was greater than 4, where k have to be bigger than or equal to 4. K have to be bigger than or equal to 4. And then we assume that this is true. We assume n equal k is true. So now we assume n equal k is true. Nice. So now that we assume that n equal k is true, Now finally, the last step is for n equal k plus 1. So what are we required to prove? We are required to prove that k plus 1 all square, this is what we're required to prove. We're required to prove that k plus 1 all square is greater than 2 times k plus 1 plus 3. We're required to prove that k plus 1 all square is greater than 2k plus 1 plus 3. So let's go ahead and try to prove this. We're required to prove that. All right, so let's go ahead and take on that. So first we have to start with what we know. What do we know? We know k squared is greater than 2k plus 3. Now what else do we know? We don't know nothing else. But if we know we have k squared and we need to get to k plus 1 all squared, what we're going to do is add 2k plus 1 to both sides. So let's add 2k plus 1 to both sides. So you notice I put it in black because we're adding 2k plus 1 to both sides out of nowhere. We're just adding 2k plus 1, so that's going to be 2k plus 3 plus 2k plus 1. We're just adding 2k plus 1 out of nowhere. So now this is what we do. And so what we're ending up getting now is this k squared plus 2k plus 1. That is now going to be our k plus 1 all square. This is now going to be our k plus 1 all square. And this is now greater than, now look at this now. I'm going to break up this as this 3. I'm going to break it up as 2k plus 2. Yeah, man. I'm going to break it up as 2k plus 2. And then the other one from this, I'm going to add that to this one right there to get another 2k plus 2. Yeah, man. Yep. Now this part right here is equal to, now this right here is equal to, if I factor out a 2 from this side, I get 2 times k plus 1 plus 2k plus 2. K plus 1 plus 2k plus 2. Now look at this. Now look at this. Remember, we were supposed to get 3. Now look at this now. Remember, k is greater than or equal to 4. That's what we know. K is greater than or equal to 4. So it is safe to say that 2k plus 2 must be greater than or equal to, this is 4 times 2 is 8 plus 2 is 10. So it's safe to say that this 2k plus 2 must be bigger than, this must be 10. So what does that mean? This implies, look how we can let all of this tie in now. That implies now, that our k plus 1 all square is going to be bigger than, k plus 1 all square is clearly bigger than, it is bigger than 2 times k plus 1 plus k plus 1 plus, now this 2k plus 2, we're going to replace it with 10 because k, it must be bigger than 10. It has to be, this has to be bigger than 10. It has to, k plus 1 all square have to be bigger than this. And this must be bigger than, this clearly have to be bigger than 2 times k plus 1 plus 3, don't it? Yeah, man, this have to be bigger than 2 times k plus 1 plus 3. Because this part and this part is the same. And the 10 must be bigger than the 3. So now we can conclude that implies that k plus 1 all square, this implies that k plus 1 all square, this definitely must be bigger than 2 times k plus 1. This definitely must be bigger than 2 times k plus 1 plus 3. Definitely must be bigger than that. Nice. Think about it. If this bigger than this and this bigger than this, then this must be bigger than this. Think about it that way. All right. If I tell you 10 is bigger than 7, which is bigger than 2, then 10 must be bigger than 2. That's how that logic's coming right here. So k plus 1 all square must be bigger than 2 times k plus 1 plus 3. Easy, soft. That's that question. So therefore, n equal k plus 1 is true. Now that we know that n equal k plus 1 is true, we could write thus, by principles of mathematical induction, you can conclude that n square, was it n square? Yep, n square is greater than or equal to 2n plus 3. And this is true for all. This is true for all n greater than or equal to 4. And n is integer. N are positive integers. We could just say natural number, but that's that. Therefore, thus by PMI, this is true for all n greater than or equal to 4. Nice and easy, soft.